Broadcast is now starting. All attendees are in listen-only mode.
Hello, thank you for joining us today for the AWWA webinar on manganese exploring treatment technologies. First, we'd like to thank our 2020 webinar sponsors, Woodward & Curran and Logistic Environmental. I'm your Milt Larson, the project manager and process engineer for Kennedy Jenks Consultants. I'll be your moderator and presenter for today's webinar. We have a few tips here to enhance your webinar experience. We recommend you close your email, instant messengers, and any other programs not currently in use, as they may interfere with a smooth reception of the webinar, causing slide buffering and poor sound quality. Technical assistance can be found at GoToWebinar technical support page at the link listed in your handouts and on the slide shown. As soon as you close the GoToWebinar screen to leave the webinar, a window will be shown with a survey questionnaire. We ask that all of you take a few minutes to answer the questions. Your feedback is important to us and helps us improve webinar programming. We encourage group participants to pick one person to enter collective responses to the survey and submit them to us. Before we hear from our speakers, I need to inform you that the mention of specific products or services in this webinar does not represent AWWA's endorsement. AWWA does not endorse or approve products or services. I'm pleased to introduce our distinguished panel of experts for today's program. Phil Brandhuber, Chair of AWWA's Inorganics Committee, John Tobiasen, Professor and Department Head of Civil and Environmental Engineering at the University of Massachusetts Amherst. I will be presenting as well. This is our agenda for today, with Phil Brandhuber kicking off, then myself, and then John Tobiasen, followed by question and answer. Our panel will be happy to answer your questions. Feel free to submit any questions anytime throughout the broadcast by using the question pane in the lower of your screen. Please include your name and in the panelists to whom your question should be directed. Let's begin. Phil Brandhuber will be covering a review of manganese in drinking water, chemistry, treatment, and impact on distribution systems. Phil specializes in drinking water quality and treatment. His work has involved inorganic contaminants, disinfection byproducts, potable reuse, and brine management. Phil received his PhD from the University of Colorado Boulder and has been the principal or co-principal investigator for 10 research projects sponsored by the Water Research Foundation and other agencies. He is the current chair of the AWWA Inorganics Committee and past chair of the AWWA Emerging Water Quality Issues Committee. Phil has 20 years of experience as a consultant working for McGuire Environmental and HDR. When not working on water quality issues, he can be found hiking or biking in the Colorado mountains. Take it away, Phil.
Manganese in drinking water, and we'll be looking at its impact on treatment, distribution systems, and I'll be talking a little bit about regulatory issues. Learning objectives for today, there's really three things I'd like to do with the presentation today. The first thing is review the basic treatment of manganese, and the point here is that we have many different ways that are effective for managing manganese in drinking water. The second thing I'd like to point out is to get a better appreciation of the issues caused by the accumulation of manganese in distribution systems. And these issues can be aesthetic, operational, and potentially there could be health-related issues to the accumulation of manganese in distribution systems. And the third thing I'd like to talk about is the current regulatory structure of manganese, pointing out that our current regulatory structure based upon the secondary maximum contaminant level is probably not adequate, and that utilities should be managing levels of manganese in their system far below the current SMCL. So with that, I'd like to start out with the presentation. As was mentioned in the biography for me, I like to hike and camp and spend time, particularly in the southwestern United States. And if you have any time spent in the canyon country, you'll have these beautiful desert varnishes that are basically manganese oxides. And certainly manganese can be a very beautiful chemical But if it ends up in your sink or in your laundry or on your wash, it's not pretty at all. And what's even more important is that recent research has indicated that there could be more serious issues than aesthetic issues with manganese, revolving around the development of children, particularly seeing reduced IQ and the potential for behavior problems. And this research has been responsible for the recent establishment of a maximum acceptable contaminant level by Health Canada for manganese, which was the first health-based regulation of manganese that we've had within the industry. So with that, I'd like to talk a little bit about manganese chemistry and sort of the key features. Really, we can get manganese into a drinking water system in two ways, as a contaminant or as a treatment chemical. As a contaminant, we basically see it in two forms. Manganese 2, which is an ion, which is highly soluble, and this is typically the form of manganese that we're treating in our raw water supplies. We can also see it as manganese oxide, typically a dioxide, Mn4, and this is the low solubility precipitate that forms and discolors water. This is also the form that's responsible for staining surfaces. As I mentioned before, we also use manganese as a treatment chemical, either as potassium or sodium permanganate. This is in the +7 valence state, the highest valence state for manganese. It's highly soluble, it's a strong oxidant. It can discolor water, it's purple in color, and when it's reduced, when we act or we use it as a treatment chemical, we typically form a manganese dioxide as the product of that, using it in our water. Now, if we talk a little bit about how manganese behaves in water, we really got to take a look at what's called the EH-pH diagram. And I realize a lot of people roll their eyes when they see this, but if you understand what's going on with this diagram, you really understand a lot in terms of how you treat manganese and also why we have manganese as an aesthetic color issue. So what we'll be looking at here is a diagram where we look at the form of manganese as a function of pH and the oxidation state of the water, with higher being more oxic water. As it turns out, we have soluble manganese in this range here, and we have a precipitate or an insoluble particulate manganese in this range here. As it turns out, in our typical water systems, we're usually floating in terms of an EH-pH combination in this range right here. So we can very easily go from a soluble manganese to a particulate manganese. We can go from uncolored water to colored water. Typically, our treatment processes depend upon manipulating the EH or the pH of the condition, where we try to move from the soluble to the insoluble and then remove this particulate generally by filtration. At the same time, too, this also explains what happens when we have discoloration of water from manganese, say in our distribution system. We have a solid form of manganese that's precipitated on the walls of pipes. We see a change either in the EH or the pH. We dissolve the manganese, and then that ultimately becomes available for discoloring the water. So if you understand this diagram, you really understand why manganese is a problem and also why we can treat it or how we can treat it. So moving away from the chemistry, I want to talk a little bit about how we can manage manganese in our sources. In particular, if we have lake or reservoir sources, surface water sources, we have a situation where there's two ways that we can control manganese, not really by treatment, by source water control. I think most people are aware if we have a lake or reservoir, that will typically stratify on a yearly basis. When the water stratifies, the bottom of the reservoir will typically have manganese sediments that release manganese into the hypolimnium, or the bottom of the lake, as oxygen and as oxygen is depleted in the hypolimnium. So one way that we can manage manganese, and I've worked on projects where this is very effective, is to use a multiple intake and withdraw water from that reservoir or from that lake away from the hypolimnium and avoid the presence of manganese. Another source water control is reservoir aeration. And I've also worked on projects like this that have actually worked very effectively as well. And what we do in this particular situation is, if we have a stratified reservoir, we inject oxygen to the bottom of the reservoir. The oxygen oxygenates the water, prevents the manganese from solubilizing into the hypolimnium, and that makes it that we can still withdraw water from the bottom of the reservoir without sucking up discolored water or water containing manganese. So these are two very effective source controls for manganese. From there, I'd like to go into treatment options. And I think actually John's going to talk about this a little bit more detail later in the presentation. But if we get to the plant, we really have a number of different options that we can use for treating manganese. And these options depend upon if the manganese is dissolved at the time it reaches the plant or if it's particulate. If it's dissolved manganese, we have the opportunity to biologically oxidize it and treat it. And I'll talk a little bit more about this in another slide. Another opportunity is to take the dissolved manganese and absorb it on a manganese oxide coated surface. This is typically called a green sand process. Or the third way to manage it is to take the dissolved manganese and oxidize it to a particulate form. We can either then destabilize it through coagulation and filtration, or if we get large enough particles, we can go directly to filtration and treat the manganese. If we have particulate manganese entering the system, it may be possible to directly remove it as a particulate, or it may be necessary to remove the particulate through coagulation and flocculation. But as you can see, we have several different ways that we can treat manganese at the treatment plant. Now, key to the treatment of manganese is typically if we use a process involving oxidation and filtration, is to use several different oxidants to oxidize manganese. And basically there's three oxidants that we can use, strong oxidants. These are permanganate, chlorine dioxide, and ozone. And I think the vast majority of the systems depend upon permanganate oxidation. And typically this is the oxidation process that works best. It's typically easy to add. It's effective for controlling manganese. Probably the biggest issue with using permanganate is one has to be very careful with the dosing. And I know I've worked on a number of projects where in fact the manganese issue was driven by overdosing permanganate and exceeding the amount of permanganate that is really necessary to complete oxidation. A second oxidant that's effective for pre-oxidizing manganese is chlorine dioxide. It's very effective. It's an excellent disinfectant. It's good for TNO control. The issue with chlorine dioxide is that the amount that you can add is limited by chlorite formation. And typically, if you have a relatively large amount of manganese and you have any other demands in the water, you're going to really reach the limit of the amount of chlorine dioxide you can add. A third oxidant that can be used is ozone. And as a treatment for a pre-oxidant for manganese, ozone has some limitations, and typically the problem with ozone is it tends to form colloidal manganese, which is much harder to destabilize and treat than, say, if you've formed particulates with chlorine dioxide or permanganate. But ozone has become a much more important issue in terms of manganese treatment because we're seeing a lot of systems moving to biological processes using ozone to stimulate those biological processes. So if you have a manganese treatment objective in these systems, the use of ozone by definition, you're using ozone as a method of oxidizing the manganese, and it's going to require a little bit more care in terms of removing it. The final thing I'd like to point out is that it's sort of a misnomer. Frequently, people feel that chlorine is an effective pre-oxidant for manganese. And as a matter of fact, if one looks at the kinetics of chlorine oxidation of manganese, generally it's too slow at moderate pHs to be effective as a treatment method for pre-oxidizing and filtering manganese. And in fact, in a lot of systems that are removing manganese that are using chlorine as a pre-oxidant, it's probably far more likely that they're removing the manganese by the green sand effect on their filter material or on their filters rather than actually pre-oxidizing the manganese and removing it as a particulate. I'd like to move into biological treatment, and this is something, like I said, is becoming a much more important issue with manganese. Certainly, as directly as an intentional treatment solely for manganese, biological treatment can be very effective. But what we're seeing more of biological treatment is it being a byproduct or a co-treatment objective as systems are going to biological filters and having a certain amount of manganese that has to be controlled at the same time. Sort of similar to the EH-pH diagram that we looked at before for chemical treatment, there is sort of a range of pH and EH values that optimize the biological oxidizers of manganese. So typically, if you're going to optimum or you're going to operate for biological treatment, you're going to have to operate in a pH range that is in this area here. Now, like I said, biological treatment can be very effective, but it's also sort of on the fussy side. And there's a number of unique considerations that need to be taken into account when implementing biological treatment. Clearly, there's a temperature dependence. There's usually a threshold under which biological activity drops off, and so the biological removal of manganese will drop off. Of course, anytime we use a biological system, there's a potential for the head loss because of the byproducts of biological activity. We have issues with biological, if the biological process is interrupted, manganese can be released. There's some issues when you restart a system about how long it takes to get the biology in place, issues with media type, empty bed contact time, and there may be needs for supplementing nutrients to make the biological process work. So again, the thinking on this here is biological treatment can be very effective, but it's also a more fussy treatment that you're going to have to be more careful in looking at. Now, moving away from treatment, I'd like to move into the fate and sort of manganese and distribution systems. And one of the key points that I want to make here is that you not only have to worry about manganese in terms of how you're going to treat it, but you have to be concerned about manganese, what happens to it once it's out in the distribution system. And we have to keep, sort of the concept here of accumulated manganese. And if we just do a quick mass balance on this system, the manganese that gets into a treatment plant is either through the raw water, maybe you've added some permanganate, maybe some chemical contamination, but either that manganese gets removed and it exits the plant from a residual, otherwise it goes out into the distribution system. And any amount of manganese that doesn't end up at the customer tap will generally end up depositing in the distribution system. And this could be quite an issue. And this was a project we worked on several years ago looking at the effects of legacy manganese in distribution systems, or the manganese that is accumulated in the distribution systems. And the point here is large amounts of manganese can accumulate in distribution systems. Manganese is easy to oxidize, it's easy to form a solid, and once it sorbs, it's pretty resilient. It wants to sorb to a number of different surfaces. The other issue you have to keep in mind too is that once manganese is in the distribution system, it can impact corrosion scales, including lead scales. Now, in a project we worked with several years ago with Water Research Foundation, we tried to sort of characterize some of the issues that involve with the accumulation of legacy manganese in distribution systems. And the clear issue here is colored water events, is that if the manganese gets destabilized, it can color the water and cause colored water events with customers. But at the same time too, when manganese releases, it also can have metals that have been sorbed to those solids that were in the distribution system. And so in addition to having colored water, there's the possibility of releasing metals at the same time when manganese stabilizes and causes a colored water event. Now, the question is, do you really get a good deal of manganese? How much manganese can you get in a distribution system? And just a rough calculation that we made, just looking here at the entry point level of manganese going into, say, a distribution system, and looking at the pounds of manganese that creates as a result of an MGD of production on a yearly basis. And if we do some quick calculations here, if we look at the current secondary MCL, for every MGD that's produced on a yearly basis, you're providing about 152 pounds of manganese into the distribution system. Even if we go to a much lower level that's consistent, say, with the guidance manual that we put together or with the Health Canada guidance, you're still putting about, theoretically, 61 pounds of manganese per MGD per year into your distribution system. So theoretically, it's possible to put a lot of manganese into the distribution system, and this manganese can, in fact, accumulate. So the question becomes, does it, in fact, accumulate? And in fact, it does. And again, looking at a Research Foundation project I worked on, With Melinda Freeman, we took some information from a prior study that she had done and give some estimates the amount of manganese that you can have in distribution systems. And this is as a function of different pipe materials and different specimens that were taken. A couple things that came out of this study are, one, is manganese can accumulate on a number of different pipe materials. And two, is actually the amount of manganese that can accumulate in distribution system can be fairly significant. The median value for the study that was done here was about 300 milligrams of manganese per foot of pipe. And if you look at this as either a 6 or a 12-inch diameter pipe, that's on the order of 3 to 7 pounds per mile in a pipe, in distribution system pipes. So clearly it's possible that a large amount of manganese can accumulate in distribution systems. And of course, once that manganese is in the distribution system, it's there and it's capable of being released and destabilized to cause colored water events and other undesirable events. Since the completion of that study, I think we've gained a lot better understanding of the impacts manganese has on lead corrosion. And this is one area where we need to be a little bit more serious thinking about what happens in distribution systems with manganese. Since the time of the study I've been talking, the Research Foundation study I was talking about, there's been a number of papers that have been published that have indicated or have outlined other issues that impacts manganese has on lead corrosion. And some of the adverse effects that you see include the presence of manganese tends to form more amorphous lead scales. These scales are less resilient and more easily released. Presence of manganese can interfere with the use of corrosion inhibitors and reduce the resiliency of scales that are formed by the use of corrosion inhibitors. I think people are aware for a long time is manganese can act as a scavenger for lead. It has a high sorption capability for lead, so once lead absorbs on a manganese scale, if that destabilizes, it can serve as a source of transport of manganese. It also can act as an electron acceptor potentially during lead oxidation and facilitate the release of lead. Probably the biggest thing to point out too is that as a manganese treatment option or a way of suppressing the impacts of manganese, we use sequestrants based on polyphosphates. And while these can be marginally effective to reduce or mitigate colored water events, the polyphosphates tend to destabilize scales in the distribution system and tend to increase the release of lead. So there's a number of different factors that the presence of manganese in distribution systems can have adversely on lead corrosion issues. Moving away from the distribution system, I'd like to just end up talking a little bit about the regulatory environment for manganese. As I think people are very well aware, there is no secondary MCL or there is no primary MCL for manganese. It's unregulated, at least in the US, based upon health effects. There is a secondary MCL of 50 micrograms per liter. There is health advisories that have been established, a non-enforceable health advisory established by the EPA for manganese. And as it stands right now from a health perspective, at least within the US, that's sort of the standard we have to look at the impacts of manganese. As I mentioned before, though, Health Canada has taken manganese a little bit more seriously than the EPA has. And in 2019 established the equivalent of their MCL for manganese of 120 micrograms per liter. And this really is the first time that a regulatory agency that at least I'm aware of has established a health-based standard for manganese. At the same time, too, Health Canada established an aesthetic objective of 20 micrograms per liter, which is obviously significantly lower than the current secondary MCL. I should point out in the guidance manual that we put together for the treatment of manganese, we recommend 15 to 20 micrograms per liter as a goal. So I'd just like to investigate a little bit about the current secondary MCL, and perhaps I'm going to be is a little bit controversial here, is that, really the secondary MCL is really inadequate at the present time. Basically, the EPA rationale, or the rationale that backs up the MCL, is purely on aesthetic effects, specifically staining, discoloration of water, and bitter metallic taste. In fact, if we go and we look at research that's evaluated where we actually see these aesthetic effects relative to the secondary MCL, what we find is that there's really no correlation between the secondary MCL and the aesthetic effects. As a matter of fact, color, I think as most people are aware, staining can occur at many times less than the secondary MCL, at least documented up to an order of magnitude less in terms of concentration than the secondary MCL. At the same time, from a color perspective, manganese too can be transparent at many orders of magnitude greater than the secondary MCL. And the taste threshold for manganese really doesn't make a whole lot of sense at all. As a matter of fact, many times greater before you can actually detect the taste from that. So basically, the point I'd like to make here is that at the present time, the secondary MCL is not only technically wrong, but I think it can be even counterproductive because it provides a degree of safety that really isn't there. It can even be misleading because in many cases, concern about manganese has resolved around if it's self-protective. If people will not drink discolored water because, or manganese water containing or water containing high levels of manganese because it's discolored. But in fact, we can have situations where there's high levels of manganese in the Mn2 form that's in the water and you can't taste it and you can't see it. So sort of a point for the utilities here is that you need to be thinking about controlling manganese to something much lower than the secondary MCL. The second thing that I'd like to point out too is comparing the health advisory, say, to the Canadian MAC. The health advisory for manganese, which is our current standard that we can evaluate health effects of manganese, was established or was finalized in 2004. And essentially, it was based upon nutritional studies that were completed from the 1960s to the 1980s. So basically, the health effects information in the current health advisory is about 30 years old. If we go look at the Canadian health maximum acceptable concentration, which was established in 2019, this is basically looking at studies that were completed in the 2000s and looking here at various impacts to intellectual development and impacts on children as the justification for the MAC. There's been considerable amount of work, not only considered in the Health Canada MAC, but in other factors as well that's looked at childhood development in the neurological impacts of childhood development. And if we look at this, there's one study I found that looks at over 30 papers published basically after the EPA health advisory that indicated issues with childhood development that are not considered in the current advisory. So what does this really mean in the future is that at this point in time, from a health perspective, we may not be able to really depend upon the health advisory as giving us appropriate guidance in terms of what the risks are for, health risks are for manganese in drinking water. So with that, I'd like to wrap things up here in terms of the learning objectives. Hopefully I've been able to point some of these things out. First is that there are many different options that are available for the management of manganese. These can be both source control and treatment. Secondly is that we really have to appreciate the issues of accumulated manganese in distribution systems. And utilities not only have to manage manganese at their source or at their plant, but they have to be concerned about how they manage it in their distribution system. And then finally, when it comes to setting what an appropriate standard is for what you control to, I'd argue right now the regulatory guidance doesn't provide a whole lot of help, and really utilities have to be thinking about managing manganese to levels that are substantially lower than what we have either through the secondary MCL or inferred from the health advisory. So with that, I'd just like to point out I've referred to a couple different studies that were done that's the source of many of these works. First is guidance treatment of manganese. I did with Bill Nockey and John Tobiasen and Sarah Clark, which I still think is a pretty good outline of the different treatment techniques and technologies available for manganese. And I'd also like to point out, if you're interested in understanding the effects of accumulation of manganese in distribution systems, work did with Melinda Freeman and Andy Hill, where we look very closely at the negative impacts of manganese in distribution systems. With that, I appreciate your time and hopefully provided some good information for people to think about today.
Thank you, Phil. We appreciate your review of manganese treatment options, some of the issues caused by manganese accumulation in the distribution system, including its action as a scavenger and its impact on other corrosion scales in the distribution system and inadequacy of the current regulatory guidance. At this point, I'd like to talk about Renton's Maplewood well-filled water quality improvements. A little bit of background. I've got a bachelor's and master's in civil engineering from Kansas State University and licensed in Washington, Oregon, and Hawaii. And I've been working with manganese treatment facilities for over 30 years. Some of the objectives for this talk is to provide a bit increased understanding of water quality issues caused by manganese and other contaminants that frequently found with manganese, such as iron, hydrogen sulfide, and ammonia. And also give you a little bit of an idea what treatment options one utility used to improve their water quality and their customer satisfaction that may be applicable to other systems with similar issues. A little bit of background on the Maplewood well field. It was developed in response to a series of underground storage tank leaks and a pipe leak and an overturned fuel truck near their major well field. Following these occurrences, the city purchased a golf course and they installed 3 wells on the golf course with a combined capacity of 5,500 GPM. And they also installed a water treatment plant and booster pump station at the site. And some of the previous work that was done when they put that treatment plant in was they installed air stripping for removal of hydrogen sulfide. And to be able to strip the hydrogen sulfide, they ended up adding sulfuric acid to drop the pH, and they had to raise the pH back afterwards with the caustic soda. They attempted to sequester the manganese that was in the water, and then belatedly they found out they had an issue with ammonia, and so they ended up with a chloraminated facility. A little bit of background on hydrogen sulfide and as to why they needed to drop the pH. As you can see, around the pH 7, about 50% of the hydrogen sulfide is present as H2S, and about half of it's present as bisulfide. But when you get up around pH 8 or so, about 90% of it's bisulfide, and bisulfide is not strippable. The only thing you can strip is hydrogen sulfide, so you have to convert it to H2S, which required a high sulfuric acid dose, and then they had a very high sodium hydroxide dose to bring the pH back up after treatment. One of the problems that resulted from this is the wells tended to go on and off depending on demand, and every time they shut down, the sulfuric acid feed that they had at the injection point would leak a little bit of sulfuric acid into the pipe, and they ended up corroding the ductile iron pipe at the injection point and had to replace it. Another problem they had was they had a lot of odor issues on the golf course, including the 19th hole where they had dining facilities, and so they were getting a lot of objections from the golfers and the diners at the golf course. And then they were also experiencing corrosion inside the water treatment facility, both the hardware and the electrical panels. And then out in the distribution system, they were having taste and odor complaints because of the remnants of the sulfide that was left in solution. In regards to the ammonia and the manganese issues, they discovered after they started up that they had ammonia. Typically, most inorganic analysis in the Northwest, they don't analyze for ammonia unless specifically requested. And so when the water is introduced in the distribution system, they discovered that they didn't have any free chlorine. And as a result, they found out that they had about 4 to 5 tenths of a milligram per liter of ammonia. And so they ended up having to segregate their distribution system. And the area served by the Maplewood supply was chloraminated, while the rest of their distribution system was a free chlorine system. And then they were also getting a lot of deposition of manganese in the distribution system. The polyphosphate sequestering agent they were using did a poor job. And so in this case, in this particular toilet water tank, you can see a lot of manganese deposits in it, and people were having deposits in their dishwashers and clothes in it otherwise. So some of the goals of the study we did was to eliminate the complaints due to manganese staining, eliminate the sulfide odors at the golf course, and improve the taste and odor of the water. And then we also wanted to produce a water that had a free chlorine residual for system-wide use, and then continue compliance with the lead and copper rule. So the treatment evaluation we conducted, we looked at manganese, and we aimed at absorption of the manganese on the manganese oxide media, followed by catalytic oxidation with chlorine. For sulfide, we looked at oxidation and also with catalytic GAC. And then ammonia, we looked at clinoptilite and also breakpoint chlorination. Then we also with the water that was sampled following the pilot plant, we did taste and flavor evaluations. So the pilot testing location was set up on the golf course between the 10th and 11th fairway. So the folks who are working out there had dodge golf balls from time to time. The two columns on the left, the taller columns are clinoptilite columns, and the 3 columns on the right there are different medias that we were looking at. And then the drop box was used for an on-site laboratory. So for manganese, as I indicated, we were looking at absorption, catalytic oxidation, and we looked at 3 different medias. Media on the left we had 36 inches of pyrolusite. The media in the center consisted of 15 inches of green sand and 21 inches of anthracite. And then the media on the right was manganese oxide coated silica sand, 15 inches capped with 21 inches of anthracite. You can either allow the manganese oxide to naturally develop over time on the silica sand anthracite, or as we did in this particular case, we pre-treated the media with potassium permanganate overnight, as suggested in a process in the an AWARF publication, removable soluble manganese from water by oxide coated filler media. The oxidant we used was sodium hypochlorite, and the pilot operation operated at 4 to 12 gallons per minute per square foot. And all of the 3 medias performed quite well. So just looking at one of the filter runs, this is run number 5, and the upper the y-axis is the concentration in milligrams per liter, and the x-axis is the time of the run in hours. And the pyrolusite and the green sand were throughout the runs were consistently below 0.01 milligrams per liter of manganese in the filtered water. And we had a few excursions with the manganese oxide coated silica sand anthracite, but I suspect if we had run this thing, the pilot plant for quite a bit longer, we'd have got more deposition of manganese oxide than the silica sand. Those levels would have come down to at time. So for run 5, we were targeting a filter loading rate of 12 GPM per square foot. And one thing that helped this was our iron concentration was quite low. So we weren't accumulating a lot of iron in the media. And so we ran the filters for about 8 days, and we had UFRVs ranging from 108,000 to 120,000 gallons per square foot. And we were operating with a chlorine dose of approximately 5 milligrams per liter. As you can see, the average manganese for all 3 medias were well below 0.01 milligrams per liter, but below what some of the numbers that Phil was suggesting. We also were able to remove most of the sulfide, and we were typically operating with a free chlorine at this time, about 1 milligram per liter in the filter water effluent. But the total chlorine was in excess of 2 milligrams per liter because we had not gone through breakpoint. In the early runs, we were looking at clinophthalite as for ammonia absorption upstream of the manganese filters, so we could reduce the chlorine demand. And clinophthalite is a high cation exchange natural resin, and it tends to preferentially absorb ammonia. It has a number of uses both in water and wastewater treatment, and it's also used in kitty litter for controlling odors. As indicated, it was upstream of the manganese filters. You can regenerate clinophthalite with about 4 pounds of sodium chloride per pound of ammonia, and we were getting about 20 days for run. We're looking at empty bed contact time of 12.5 minutes, and we got good ammonia removal when we're operating at 3 gallons per minute per square foot. However, when we tried to load it at higher rates, the performance deteriorated. And we eventually switched away from the clinophthalite and just looked at breakpoint chlorination for ammonia removal. The ammonia, we had a high and variable chlorine demand with the theoretical demand to get through breakpoint is 7.6 parts of chlorine per part of ammonia. And our bench study indicated we were operating a little bit over 10 parts per part. And it required some significant manganese filter contact, post-manganese filter contact time. We initially started out targeting 0.5 to 1.0 milligrams per liter free chlorine in the manganese filter effluent, which is commonly used for absorption catalytic oxidation. What we found is samples collected in the evening, we come back in the morning and measure the chlorine again, and we had very low or no chlorine residual remaining because the breakpoint chlorination was continuing. It was incomplete going through the filter. And so as a result, we increased our treated water chlorine residual target. This is a decay curve from one of the bench scale runs we had with time on minutes on the x-axis. So we started out with free chlorine or total chlorine in excess of right around 2.5 milligrams per liter, and as the breakpoint reaction continued, it closed in on the free chlorine, and so we ended up selecting a chlorine contact time of about 90 minutes to go through breakpoint. So some of the sulfide removal options are that you can look at. One is aeration, which in the case of Renton, they were using, and they were dissatisfied because of the odors that they had, plus the high acid and base requirements it had. Another option is a method is oxidation. Typically, depending on the reaction, it requires 2.1 to 8.3 milligrams of chlorine per milligram of sulfide. Depending on the endpoint, 2.1 is when you're converting to elemental sulfur. However, a lot of times you end up producing polysulfides and salt as well as sulfate. And Muskowitz and Ainsworth had developed a methodology for treating polysulfide formation, which we felt was probably part of their problem. And that involves the addition of sulfite followed by which converts the polysulfide to thiosulfate, and followed by rechlorination. And then other options are, if you're able to just oxidize it to elemental sulfur, they just remove it by filtration. And then the one we settled on was catalytic GAC. So with catalytic GAC, we put that in front of the chlorination process. Basically, the catalytic GAC absorbs the sulfides, and then in the presence of dissolved oxygen, it catalytically oxidizes it to sulfate. An excess of dissolved oxygen is required because you need to maintain an aerobic condition throughout the GAC bed. Because if the lower part of the bed happens to go anaerobic, you can always convert the sulfate back to sulfide. We were looking at an empty bed contact time of 3 to 5 minutes, and we were reducing the sulfide from 0.12 milligrams per liter to 0.002 milligrams per liter. typically a backwash, the GAC at about 8 to 10 gallons per minute per square foot. The bed will go biological, so you will have biological growth in the bed. So one of the things we did was after each of the filter run, well, once a week, we would have a panel that consisted of city personnel and interested customers from the Maplewood service area do a simplified taste and flavor evaluation. Quite a bit simplified versus what has been published in some of the AWB publications. And basically, we had them do a blind taste test and rank it from 1 to 5, varying from awful to very good. And then for waters that were identified as mediocre and below, we had them give us their idea of what the taste or the flavor they were observing. So the different waters we had ran the taste and odor or taste test on was we used bottled water as a control. They also took water from City Hall, which was getting water from their other major well field, which people seemed to like, and that was more or less our gold standard. We also took water from the Maplewoods at City Shops, which was receiving chloraminated water from Maplewood, and then water from the different pilot filters, clinoptilite only, then clinoptilite followed by absorption catalytic filtration, clinoptilite followed by absorption catalytic filtration, plus bisulfite addition, then rechlorination, and then lastly GAC upstream of the manganese filtered, followed by breakpoint chlorination. So the average of the test stores or the study, the bottled water was, they considered that the good tasting, and the water from City Hall they liked. When they got to water that was from the chloraminated system, it dropped down to kind of mediocre range. And then we were getting quite poor results in terms of flavor now, or taste and odor scores for the pilot filters coming from the pyrolusite or the green sand or the silica sand. Although the numbers did tend to prove, you know, if the water was held overnight and tasted the next day. And as a result of this, we ended up switching over our treatment regime and looking at both the methodology used by Ainsworth and Muskowitz for treating the polysulfides, and also we looked at green GAC to catalytically oxidize the sulfide prior to green sand, followed by breakpoint chlorination. Based on the results, we ended up installing a side stream aeration for the water coming into the treatment plant to raise the dissolved oxygen, followed by catalytic GAC, converting the sulfide oxidation to the sulfide to sulfate. Then we chlorinated the water and went through absorption catalytic oxidation to remove the iron and manganese. Followed by that, we had breakpoint chlorination with a 90-minute contact time, and then they were able to rechlorinate and send it out into the distribution system. Some of the lessons learned, it's not surprising. Manganese sequestering performed quite poorly. A number of people have referred to manganese sequestering as just kind of putting a Band-Aid over the manganese and just hoping you can keep it sequestered while it's in the distribution system before it causes any aesthetic issues. We were able to get fairly high manganese filter loading rates with all three media. That was probably helped by the fact that our iron was quite low, which tended to limit the clogging of the media. We did get biological growth in the GAC early on. The city didn't backwash fairly frequently on the GAC, and they did get clogging of that media. So after the first year, they end up replacing the top 12 inches of the media, and they increased their backwash frequency to weekly, and they haven't had any issues since that time. Feel that including customers from the area receiving Maplewood water in the taste and odor panel was beneficial and helped them buy into the project. Kind of like to acknowledge some of the people who helped us on this project: J.D. Wilson and Ray Sled, from the City of Renton, and Greg Pearson from HDR, who is our partner on the project. I'd like to remind you to submit your questions using the question panel anytime during the broadcast. John Tobiasen will be covering creative process combinations for simultaneous control of manganese, iron, and disinfection byproducts. John Tobiasen is a professor and department head of civil and environmental engineering at the University of Massachusetts Amherst. He has a BS in civil engineering from the University of New Hampshire, an MS in environmental engineering from the University of North Carolina, Chapel Hill, and a PhD in environmental engineering from Johns Hopkins University. He's the past president of AASP and past chair of AWWA's Water Science Research Division of Board Trustees. He's a registered engineer in New Hampshire and a board certified environmental engineer by AAES. John, take it away.
Okay, thank you, Milt. Appreciate the opportunity to share some thoughts about manganese control with our audience. Thank you all for attending, and thank you, Phil and Milt. I'm going to present a lot of information fairly quickly, and for the participants, you'll be able to look through it in more depth with the handout, with the PDF you can download. So my task was to look at some treatment combinations, particularly when we have multiple things going along with manganese. But to say a couple of things, let's see. My slide is not advancing. There we go. First, a couple of comments. When you throw in iron discussion along with manganese, our industry tends to say the words iron and manganese like it's one word, and that things are the same. And they're really different. They're different elements, and we need to be careful about that. Also, another point is that while iron and manganese treatment is common, the complexities are often ignored and a lot of myths are perpetuated. So important to pay attention to the cases for the situation for your particular treatment facility or source water. And I'll point out some things about characterizing the forms of iron and manganese a little bit. That's very important to understand what's going on. And that I think if you think fundamentally about what's going on in treatment plants from reaction and transport of water and particles and other things and dissolved constituents, you can come up with some creative approaches that work based on the data for your facility. So to me, removal of iron and removal of manganese can be simplified into either become a particle or get to a surface. Becoming a particle usually involves adding an oxidant or making use of one that's available. We make various kinds of particles, and we do our particle removal steps, which need to be tailored to the particles we make. Or dissolve iron and dissolve manganese, which is usually the form they're in our source water when we're considering them a problem. In their reduced Mn2 and Fe2 form, get to a surface, and we'll talk about those surfaces in a minute. They come off those surfaces, residuals, and we can get some great removal. Now, we also have to throw in natural organic matter and other constituents. Milt just talked about sulfide and ammonia, but those constituents react with oxidants, anything else we add, and also with the particles and media surfaces. So we have to keep all those things in mind when looking at complicated systems. So Phil showed a version of this figure from the guidance manual. This is a version of a figure that's in a paper that's focused on manganese that we wrote, but you can expand it to manganese and iron, which again focuses on first you have dissolved the particulate manganese, as we look here. If it's particles, we go a particle removal path. If it's dissolved, we either make particles and go that path, or if it's dissolved, we can take up on various surfaces. And we'll look at that in our treated water goals. We can also have combinations of particle removal and going to a surface removal, and that's usually for particulate iron and dissolved manganese in the same filter. So let me focus this path for a little bit on the particle removal side. So a couple of schematics, we might have groundwater that we have an oxidant. Phil mentioned in his presentation that strong oxidants are needed for manganese removal in this scenario, whereas weak oxidants like oxygen and pre-chlorine are very effective for iron, but are not effective for manganese at the typical pH and time frame we have in treatment plants. It's not always true, but often is. So we need time, and then we can filter those particles out, usually with a media membrane filtration, and sometimes we have clarification in between. For surface waters, it's more common to have perhaps coagulation, flocculation, some kind of clarification step, and then to media or membrane filtration. So these are some schematics that we might come across. I stress the importance of knowing the form of the constituent, iron or manganese. So in the raw water, knowing the forms help us guide our selection and design of processes and operation. And then if we want to look at what happens when we do any kind of chemical addition, oxidant, pH, coagulant, then we need to know the form because it controls performance of the subsequent process. So it's important to make this. And distinguish forms, and some people use the word species for this, as particulate, colloidal, and dissolved. And usually we use some kind of somewhere in the 0.2 to 1 micron range membrane filter, call those particles that are greater. And things that pass through that and are greater than a 32K or 100K molecular weight ultrafilter, which is on the order of 1 or 2 or 3 nanometers in size. Those we call colloids, and what passes through is we call dissolved. And you do this in a lab with a syringe filter for particles, and then you need a pressurized cell with nitrogen and an ultrafilter to do this distinction to dissolve versus colloidal. And that's the hard part, because no commercial lab does this, and a few academic labs and researchers do it, so it's challenging. The good news is that you can coagulate those colloids and use this simple separation technique to also distinguish between them. And in fact, it's important at full scale, that aggregation phenomenon. So as one example of treatment, this is some treatment of manganese, about 0.06 milligrams per liter in some raw water. And this particular plant uses pre-oxidation, full scale with permanganate, followed by coagulation, followed by direct filtration. And this is just an illustration that if you don't add an oxidant, you don't remove any dissolved manganese. If we add ozone, we make some colloids and particles, and then when we coagulate, flocculate, we make particles and remove them. And then particularly with permanganate, we make a lot of colloids, and then they become particles with coagulation, flocculation, and we remove them. And the point here is that if we didn't measure this fraction, if I took out my syringe filter and measured dissolved manganese, which would be everything below here, I would think I had a lot of dissolved manganese, and I'd add more oxidant maybe to remove that. It would be exactly the wrong thing to do. It would make the problem worse. So having this distinction can be very important in operation and understanding of what happens across treatment. So the first thing to do is to go across the treatment plan and figure out what the forms are and what's going on. So the two mantras about adding chemicals to anything that you want done is how much and how fast. And stoichiometry is how much, that's the fancy word, how much iron or how much oxidant you need for iron and manganese. And at the end of this presentation, I'm not going to show it, I have tables of the stoichiometric demand of different oxidants per iron and manganese. And it turns out you need twice as much oxidant for a milligram of manganese than a milligram of iron. That happens to be because of a 2-electron transfer crate for manganese and 1 for iron, but they happen to have similar atomic weights. You also have to add an oxidant to satisfy competing demands. And then when you do make particles, I already mentioned this, there can be some unusual effects of those particles on other dosing, so you need to follow that. Kinetics just means you need enough time. And enough time depends on the oxidant, the pH, the temperature, and competing demands. So again, it can be case specific. It can be extremely fast, or it can take a while. I'm going to talk about some things with iron oxidation versus manganese oxidation that we can take advantage of to do some particular treatment, treatment process for a mixture. So iron is really fast compared to manganese, so the oxidant is going to go there first, and then we can have some other options, which I'm going to describe. So here's an example where we have iron, manganese, and NOM. So we have a water, I say raw here, could be any water. We dose an oxidant, could be any of those. And what's happening here is that we have multiple parallel reactions. And multiple parallel reactions means that the fastest reaction wins. So, and the rate depends on the levels of the reactants and the fundamental kinetics of that reaction rate. So I've shown here iron 2 with an oxidant, manganese with an oxidant. We want them to go to particles, oxidize. NOM with an oxidant, which might form, depending on the oxidants and disinfection byproducts we don't want, or oxidized organic matter. And then the NOM gets a chance to react with the metals that are precipitated, iron and manganese. So there's a lot going on here. And one thing I want to point out is that we don't get to choose which one of these occurs. They happen because of the fundamental concentrations and fundamental rate constants for the conditions we're at. So we need to be selective and carefully engineer and operate systems to achieve the outcome we want. One example of that is with chlorine and water with iron, manganese, and NOM. I'll show you a plant later on that uses some of this. So if let's dose chlorine, and we've got iron 2, manganese 2, and NOM in there. Iron 2 reacts with chlorine and makes iron hydroxide. Manganese, in principle, can react with free chlorine and make manganese oxide. And NOM and free chlorine, we know, make some DBPs we don't want. But we're lucky in this case in that the iron-free chlorine reaction is so fast that if we're careful with our dosing and just add enough chlorine to precipitate the iron, we don't get any DBP formation. So we can get iron oxidation with an oxidant we know how to use and it's relatively inexpensive, and no for creation of NOM, of DBPs. A couple of things that can happen though is that one is that we now need another approach for manganese because we haven't removed any manganese here. We haven't changed it from dissolved. And two, the natural organic matter can interact with the iron particles that are precipitated and might create some stable colloids that we have to deal with downstream depending on our treatment process. So parallel reactions, fastest wins, and we can do some management and control of that. So in terms of dealing with dissolved manganese in another manner, we can move on to using surfaces to remove dissolved manganese and dissolved iron. So the fundamental simplified concept is we have dissolved iron, dissolved manganese. It's going to enter some tank or bed of granular media. Milt already actually presented a lot of different names of different media that we might use. We have metal cation uptake on the media surface. And that media surface could be a metal oxide, like manganese oxide. It could be an ion exchange media, or it could be the biofilm of a biological process. In either case, it's a dissolved iron or dissolved manganese getting to a surface and being removed via that surface. So a couple of ways we've described that in this chart are highlighted here. We've got ion exchange with the waste brine contains iron and manganese. We've got biological oxidation and media absorption there. And both of those lead to particulate residuals. So I'm going to focus for a minute. I'm going to ignore the ion exchange and the biology and just focus on media absorption kind of a approach, which I also referred to as well. So in terms of the fundamentals of that, it's a two-step process where the dissolved cation is absorbed to a surface, and here I'm using a manganese oxide surface because that's really effective for manganese absorption and iron absorption, and it removes the dissolved species. But out in solution, we might have an oxidant, or we might apply it when it wasn't there, and it regenerates the media surface by oxidizing the metals on the surface, creates a new oxide surface that can do more uptake, and so we often call this an autocatalytic process. We can recreate the surface we want or oxidize the surface we want by two fundamental methods. One is continuously, and the other is intermittently. For continuous, I mean the oxidant's always in the influent, and so we can get we have the oxidant in the influent. If the oxidant oxidizes the reduced metal in solution, then it creates a particle, and now we have particle removal, not absorption. For the Mn, manganese and an oxide surface, free chlorine works well because it's too slow to oxidize it in solution, but really oxidizes it fast when the manganese is absorbed. Oxygen does not work in this same manner, unfortunately, which it did. And strong oxidants can work in principle by this mechanism, but usually oxidize the metal in solution to make a particle. So for iron removal, Iron removal is typically mostly by particle formation and deposition when we have continuous oxidants in the feed. In contrast, intermittent regeneration can be used. So this would be typically an intermittently regenerated green sand type media where the manganese and the iron are absorbed. We apply at backwash, we apply a potassium permanganate solution. It oxidizes the metals on surface, removes a bunch of those oxidized metals, and we go back and do sorption again. So there's kind of three places where we see this approach being used in treatment facilities. One is what I'll call a typical green sand filtration approach. I don't tend to actually like the word green sand, but we don't have time to get into that. We use manganese and iron can be removed and either intermittently or continuously. So we often have combined iron particle removal and MN sorption on surfaces when this is employed. Oxide-coated media filtration. This is often in the case of surface waters where, if you look back in the late 80s, early 90s, Bill Mackey got going on this topic, and in fact referred to literature from the 60s where we often had silica sand that became black and it was sorbing manganese and having it oxidized on the surface by free chlorine. So the primary job of the media here is to remove particles, but also take up manganese. And then the third case I'm going to give you an example of is where we don't ask the media to do any particle removal, but simply ask it to take up dissolved manganese and have sorption occur on the surface, and I call that a manganese contactor. So the typical green sand approach is that we may or may not have a preoxidant, or we typically, we may or may not, but if we have with preoxidant, we have maybe free chlorine or permanganate, and it might oxidize it before it gets to the filter, that then we have particles. And that would be the case with a strong oxidant, but usually not a chlorine for manganese. And iron usually becomes particles. I have a couple of points here about permanganate. We basically can't really afford to have much permanganate or any entering a media filter, because then we risk having that media in the effluent, or colloids that result from the reduction of the manganese, the permanganate Mn7 to Mn4, and those leaving the media. So it's a difficult place to be. I think a lot of utilities and people who add permanganate ahead of these filters think that permanganate is getting to the media, and the only time I know that it really is when they have a pink water problem, because it goes through the media. We just don't often measure what's going on. For media regeneration, I mentioned continuous with free chlorine is effective, but getting permanganate to the surface continuously is a risky business. And intermittently, we often use permanganate, most likely. The oxide-coated media in filters, we've done a few publications about this. Milt referred to one of them. That Bill and Aki and I did a study of a lot of media filters. It's an AWRF publication. And Milt referred to a procedure there for coating that I'm going to comment on in a minute. But here again, we asked the media to take out particles, but also do manganese oxide, manganese removal. It's extremely robust, works great as long as we carry a chlorine residual through the media, but there's some concerns. One is if you don't carry that chlorine residual through, you might release manganese, and the other is that we've learned that we increase DBP formation by applying chlorine ahead of the filter instead of after the filter, basically due to continuously exposing sorbed or media-related NOM to new chlorine, and we can make more DBPs. So one approach to get rid of that problem is to first remove as much NOM as possible, and then use a contactor that only sees free chlorine and is asked to remove dissolved manganese. We call it a post-filter contactor, or a third stage contactor, or second stage, but it can work very, very effectively. And we have an example I want to show you about doing this. So this particular case is one that we wrote a paper about January 2016, AWWA, and it's the Lantern Hill Plant Aquarium Water Company in Connecticut. And prior to 2013, it was a single-stage direct filtration plant with free chlorine, permanganate, base, and polymer added, and an anthracite over green sand media filter. And we found that we had to have a really significant free chlorine residual leaving the filter in order to avoid manganese release. And unfortunately, that combination of things basically made that filter a DBP factory, produced very high levels of DBPs. So through pilot studies and lab studies, we worked with Aquarian, and they built a full-scale plant that came online in July of 2013 that moved to 2 stages. So this is a case with, unlike the one that Milt mentioned, has a lot of iron, a reasonable amount, 2.5 milligrams per liter of iron, about 1/10 of that of manganese and some TOC. We can add a preoxidant, either free chlorine or permanganate, to oxidize the iron. And with free chlorine, you have to do it carefully so you don't make DBPs. It has to be just enough to oxidize the iron. The cationic polymer directly precipitates some of the NOM and aids in particle removal, and the base is there to raise the pH to about 7.5 from 6.5 in the raw water. Then it goes through dual media filtration for particle removal, takes care of all the iron and some NOM and enough NOM that we then add free chlorine to a manganese oxide chromic coated ceramic media that's about 2 millimeters in diameter, 40-inch bed depth, and operated at 10 GPM per square foot. And it doesn't make any head loss, but every 4 to 6 weeks or so it gets backwashed. The media looks like this over here, and the coating procedure used here was, I think I'll give Derek French credit for this, is instead of just the permanganate approach that we've used for anthracite coal over time, when you try to do that with ceramic media, it doesn't work so well because there's nothing on the surface to reduce the oxidant, for the oxidant to react to it. Instead, here we put on manganese sulfate, soak first, and then 2 goes to the surface. Then we add the permanganate, which oxidizes the adsorbed Mn2, and we make a great coating with that procedure. Repeated it many times and just about any media you want. So here's some profiles of constituents across the plant. This is iron, and so here's the raw water. It's all dissolved. We add an oxidant, make it all particles. The particles don't come through the dual media filter, and that's the iron story. So end of the story. Dissolved, particles removed. Pretty typical for iron. Manganese switches where we have dissolved manganese in the influent. We add that chlorine or permanganate to oxidize the iron, but it doesn't make any, it makes a little bit of colloids, but not much. And it goes right through the dual media filter because it's dissolved, and that's what it's planned to do. Then we add chlorine right here. Contactor influent is still dissolved, but the contactor effluent is all gone. And that's how the manganese is removed. And the real story is that we don't make DBPs up front. The dual media influent and dual media effluent, where we've added chlorine to oxidize iron, are low. And then we add chlorine, and we do get a DBP formation here. And from the historical results, where sometimes HAs and THMs were extremely high when the new plant went on, they were much, much lower. So that was the approach used there to deal with iron, manganese, and DBP control. The last case I want to show you is one here that is being built or just went out to bid and will be built in 2020 and 2021. Is up in Maine for groundwater at the Brunswick Thompson Water District, Jackson Station, where the current process is a single stage of intermittently regenerated manganese oxide media, green sand, with no NOM removal. Here, there's a moderate levels of iron and manganese and some TOC, but there was a THM production problem. So they looked to solve this. So after extensive piloting of a variety of options, we ended up at a place that I had been involved in this project from the get-go and did not think we'd get to, but it turns out that it's a 3-stage process with 3 different surfaces. First is the intermittently regenerated manganese oxide surface. They decided to stay with that to remove all the iron and most of the manganese, but it is fundamentally a breakthrough curve system, and you can't maintain 10 to 20 microgram per liter levels very well by this approach. Then the water passes through a fixed bed anion exchange to remove NOM, the DPP precursors, which also doesn't remove any more manganese. And then free chlorine is added, and the water passes through a 3rd stage, a manganese contactor, which in this case is 36 inches of manganese oxide coated anthracite, which is done by that same method I mentioned for cerulite. Operated up to, we tested up to 25 GPM per square foot, and that'll be to polish the manganese down to very, very low levels. So those are my examples, and I just end you with some slides that you can think about, which I like to think about manganese and iron control from two perspectives. One is a co-constituent perspective, and the other is a process perspective. So if you have manganese or iron only, a lot of options, few constraints. Manganese and iron, you need to think about the fact that iron is going to be oxidized first, and oxygen and HOCl can be effective for iron, but not manganese. NOM has a oxidant demand, GBP precursor, impact size and stability, and so you have to take that into account. I didn't mention this, but arsenic also is one that is interesting when that occurs in groundwater, because we can oxidize AS3 to 5, which then is removed better by iron oxides, which may also be precipitated, and arsenics and oxyanion, which could also be removed by ion exchange. Radionuclides present some particular questions, and then if we have a lot of hardness, the calcium and magnesium are going to be important because they're going to be removed in ion exchange process. They do precipitate at high pH, and they have a chemical demand. So lots of fun, parallel oxidation reduction, precipitation processes. I guess my point here is that don't expect it to be simple. Don't expect generalizations. Look at the source and act appropriately. Then the other side of this is your treatment objectives. If the objective is primary disinfection, then your selection of oxidants you need to take that into consideration, whether the oxidant is or isn't also a disinfectant. And then if your disinfectant is UV, for example, well, you better not have iron and manganese around to get oxidized and put foul sleeves. With coagulation, we have the opportunity to destabilize an aggregate iron and manganese particles so that they can be removed by processes that require destabilized particles. But on the other hand, if we have a treatment process such as MF or UF membrane filtration, we don't need to have destabilized particles. We just need to make particles by effective oxidation. Intermediate ozone is an interesting case of where ozone might effectively oxidize manganese that didn't get oxidized earlier, and it may create manganese particles that need to be destabilized prior to media filtration. The problem is it's after you've done coagulation, so you need to do coagulation again. The manganese colloids don't get removed well by filtration, not because they're small. Media filters remove molecules, remember, really well. So they don't need to, it's not because they're small, it's because they're stable and they don't attach to the media. Particles, then again, the selection is there. And if you want to have biofiltration, then that kind of eliminates sorption and catalytic oxidation with free chlorine on the biofiltered media. But there's other media processes that can be used. So with that, I want to thank all the learning I've done with Bill Naki and my students and the water utilities I've worked with and my colleagues at UMass. So thank you.
Thank you, John, for highlighting the benefits of characterizing the forms of iron and manganese and how that impacts the treatment process selection. Also on other treatment objectives, how they impact iron and manganese control. So far, we've got 2 questions. I'm not seeing the questions yet.
All right, I'll go ahead and get those asked then. So Walter Palmero was asking, would you recommend to apply an oxidant permanganate prior to or after lime for pH adjustment? And any one of y'all can handle that.
Well, I'll jump in. I mean, if you can get the pH up, every oxidant works faster. So that's an advantage of after pH adjustment with lime. But Phil or Milt can speak better from a practical side.
I would think if you're trying to absorb onto manganese oxide coated media, you may want to do it afterwards. but if you're not doing an absorption process before. There have been some cases where if you've got high pH and elevated silica, that's been shown in some cases to interfere with the process.
All right, and then the second question comes from Laura Mateer. This is for John, and the question is removal method 2. Does the chlorine residual have to be free chlorine or can it be a chloramine? Wondering if the ORP/EH would be less desirable for a chloramine.
So 2 meaning sorption and catalytic oxidation, I think, is what's meant there. Is that, I assume that's the question. So that's a very interesting one because Bill Mack and I have just been talking about that recently. We actually realized we never had a student study the sorption and catalytic oxidation process with chloramine, but Bill's student is doing that for Bill right now. And we think there is some effectiveness of chloramine across the media. It doesn't happen very often, but I think there is a possibility for that to happen. I don't have any direct experience, but like I say, we're getting it. So it's some of that's being obtained right now. Chloramine is not going to oxidize manganese in solution. It's weaker than free chlorine. The question, I don't think it'll be as effective as free chlorine, but there might be the right time and pH conditions that make chloramine oxidation of sorbed manganese effective. So I guess it's a qualified maybe.
Awesome. Okay, we have another question here from Chris Catlin, wondering how does the pure flow process work using chlorine to oxidize manganese and filter at very high rates?
What was the first word you said? How does the what process
The
work?
pure flow process.
Pure. Not familiar with it. Phil, nope. Either of you guys heard that?
I think you may be referring pure flow similar to Filtronics. Basically, that's
there's a couple of proprietary systems that are similar.
Yeah, and so that's an absorption catalytic oxidation process where the manganese is absorbed onto the media, and then in the presence of free chlorine with an elevated ORP, it oxidizes the manganese to manganese oxide.
All right, let me see if there's any more here. It looks like I've got one more here. And I'm going to butcher this last name, so I'm just going to say the first name here. But the first name is from Lakshmi. And the question is, what is the approximate reaction time for manganese oxidation?
Months to microseconds. That's what.
Yeah.
It depends on the oxidant and the pH. That's just the facts.
Yeah,
So,
it can be very fast, but if you're in like natural environments and you have long periods of time, you can even get it oxidized with oxygen.
extremely long time. Yeah, right. Or if you have some manganese oxidizing bacteria around, they're handy. So there's no, it's a wide range.
Let me see what else we have here, because we have a couple more minutes here. Let's see. Actually, I will send this one. There's a pretty lengthy one, so it looks like a little bit of calculations and whatnot. I'll send that on over to you guys because I obviously don't want to mess that one up. So we'll reach out to Troy and Troy Hotchkiss and get him an answer on that. So there's a lot going on there. And I am no expert, so I don't want to mess up that question there. Let me see if we have anything else here. Let's see. We have a question from Camilla asking what conditions promote manganese release from pipe scales?
I guess I will this is Phil. I guess I'll go ahead and try to take that. Is that you can get a number of different conditions. Is generally the more depleted your residual is, the lower the ORP is going to be in the system, and you can get release that way. Changes in pH, a rapid decrease in pH is a pretty good recipe for releasing scale. There can also be physical issues there in terms of changes in flow velocity or changes in flow direction, which will end up physically destabilizing the scale. So there's a whole range of things that can end up resulting in the destabilization of the manganese scales and just scales in general.
All right, we'll take one more and then we'll wrap it up here. Another question from Laura Mateer. She says, can any of the presenters comment on the interference of ammonia due to manganese removal?
So with adding the ammonia, you're going to be forming chloramines. And as John indicated, a lot of cases with chloramines, it's not nearly as effective as free chlorine in oxidizing the manganese on the filter media. And plus, it's got a huge chlorine demand. You're talking approximately 10 parts for 1 part, a little bit more than the theoretical dose. So a lot of waters I've seen up in the Northwest, we have maybe 3 or 4 tenths, 5 tenths of milligram per liter of ammonia. And so that has a large demand.
Yeah, that's what I would say too. It's the oxidant demand side of that is huge. I mean, the nitrogen there is in a reduced state, so most places we want to get it oxidized. The good news, I guess, Phil, you didn't mention it, but manganese, oxidizing biofilms can oxidize at least nitrified ammonia, but then there's a question of what comes next.
All righty, so we'll go ahead and wrap up the Q&A there. Milt, if you want to go ahead and wrap us up, that'd be great.
Okay, well, I'd like to thank Phil and John for their presentations. This concludes our webinar on manganese, exploring manganese treatment technologies. Before we go, I'd like to mention the upcoming webinar series. AWWA hopes you join them for the remainder of the Contaminants of Concern, Managing Lead and Manganese webinar series. The remaining schedule is as follows. It's indicated on the screen here. Regulatory concerns and updates on inorganic contaminants webinar on May 19th. Corrosion control with contaminant of concern, managing lead and manganese, May 22nd. And then on May 26th, strategies for understanding and managing risk from lead contaminants of concern, managing lead and manganese. If you register for the entire series bundle, May the 12th webinar will be available as well. For a full schedule for the 2020 AWWA webinars, go to awwa.org webinars. Let's see. As part of your registration, you're entitled for an additional 30-day archive access to today's program. Until next time, keep water safe and secure. There is a survey that we'd like you to fill out following this session. Please appreciate it if you go ahead and do that.